Welcome back, business calculus students, to our online midterm review videos. In this video, I'm going to work problems concerning continuity and instantaneous and average rates of change. So I'll be working problems 9 through 12. Have your midterm review worksheet handy and ready to go, and you can work through these problems together with me. Problem number 9 says, consider the function f of x equals x squared minus 9 over x times x minus 3. Find all values x equals a where the function is discontinuous. So we're going to be looking at this function. Notice it's a rational function or a function that looks like a fraction. We're going to be examining what values of x create a 0 in the denominator. And if we inspect this carefully, there's going to be two places in the denominator where we can plug in a value of x to cause the value of that denominator to be 0. And the denominator in this case is already factored, so if I set each of those factors equal to 0, I can find out specifically which values of x cause the denominator to be 0. So we have a discontinuity at x equals 0 and at x equals 3. These are two different types of discontinuities, as we'll see in part B. It says at each value x equals a, where the function is discontinuous, give the limit of the function as x approaches a. Be sure to note when the limit does not exist. So if I look at the original function, it's going to be really helpful to have the entire thing factored. So let's go back and do that. In factored form, f of x looks like, notice we've got the difference of two squares here, x plus 3 times x minus 3 over x times x minus 3. Now when you have it in factored form, it's almost irresistible to want to come up here and cancel out those like factors. Notice when I do that, I am removing the factor from the problem. When I remove that factor, the remaining fraction will allow us to calculate the limit by direct substitution. So let's start by finding the limit of this reduced function as x approaches 0. So we have the limit as x approaches 0 of x plus 3 over x. Well, I chose the hard one first. We should have done 3 first. Well, we'll start with the difficult one, and then we'll be home free when we evaluate the limit as x approaches 3. Now, after I have factored the fraction and reduced it, I've removed that factor x minus 3, we still end up with a 0 in the denominator, right? If I plug the target value in for x, I still have that problem. If I attempt to apply the two techniques that we practiced in the first video, where we factor and cancel or we rationalize, neither of those are going to help us on this particular problem. So we're going to really have to think about what is the limit. The way I'm going to figure this out is by thinking about x approaching 0 from the left and from the right. And then don't fear, we will verify this on our graphing calculator. So if I think about a number line, when we evaluate the limit as x approaches 0, we're trying to figure out what's the general behavior of the graph on both sides of 0. So as x approaches 0 from the right side, notice I would be dealing with all positive numbers. So if I'm plugging a positive number in for x here and a positive number in for x here, I can tell that my entire fraction is going to be positive. So keep that in mind. The sign of our fraction on the right side of 0 is positive. However, as the numbers get closer and closer to 0, I know the numerator looks like 0 plus 3, and the denominator looks like 0. So essentially, I have 3 divided by 0. As the denominator gets smaller and smaller and smaller, and that numerator stays constant at 3, the value of the fraction explodes to infinity. So we can say the limit as x approaches 0 from the right is infinity. Okay, so let's make a note of that. Limit x approaching 0 from the right of our function is infinity. So technically the limit doesn't exist. We're just saying that the function is exploding on the right side of 0. Let's consider the left side of 0. As x approaches 0 from the left, notice we're going to be dealing with negative numbers. Okay, and we're looking at numbers very, very close to 0. So if I plug a negative number in for x, I notice my denominator is going to be negative. It's a different story in the numerator. If I plug a negative number really close to 0 in for x and then add it to 3, I'm still going to have a positive numerator. So I have a positive on the top and a negative on the bottom. So keep those signs in mind. However, x is approaching 0. So the essential value of the numerator is 0 plus 3, or 3, and the essential value of the denominator is getting closer to 0 from the negative side. So we have this same issue, 3 divided by 0. The value is exploding to infinity, but because of our sign differences, we can say the limit as x approaches 0 from the left is negative infinity. If the value of the limit on the left is not the same as the value of the limit on the right, we say the limit does not exist. So we'll say the limit as x approaches 0 of our function, I'm going to abbreviate this DNE, does not exist. You are welcome to do that on your review worksheet and on your midterm exam as well. Now that was a hard concept, so let me give you a visual to help you to digest all that information. Let's go to our graphing calculator and type in y equals, and we'll enter our function. So I'm going to include the numerator in parentheses so that the calculator applies the correct order of operations. So there's my entire numerator, x squared minus 9, divided by, and I'm going to enclose my denominator in parentheses as well, x times x minus 3. Notice I'm plugging in the original function before we reduced it. That way we can examine our other limit here in a minute. After we've plugged in the correct function, let's type our zoom button and choose number 6 standard. That way we're all looking in the same viewing window. Okay, so here's our rational function. Notice we have a vertical asymptote or a boundary line right there on the y-axis. So let's talk about what does the function value do as x approaches 0 from the right and from the left. So as x approaches 0 from the right, what's happening to the function values? The y values are going where? They're exploding to positive infinity. On the other hand, as x approaches 0 from the left, what are the y values doing? The y values are plunging down into negative infinity. So because the left side is going in a different direction than the right side, we can't say the general behavior of the function approaches some target value, some limit. So we say the limit does not exist. Okay? Let's try the limit as x approaches 3. Now remember, we took our original function, we factored it, and we reduced it by removing this factor x minus 3. Now, when I calculate the limit as x approaches 3, I can do so with the reduced fraction. This one's going to be a piece of cake. We can evaluate it by direct substitution. No zeros in the denominator creating issues here. So we have 3 plus 3 over 3. Again, when we evaluate the limit, we drop our limit operator. This gives us 6 over 3 or 2. So the limit as x approaches 3 of our function is 2. All right, so let's verify that with our calculator. If we go back to our graph and we examine what happens to the y values as the x values approach 3, here's 1, 2, there's x equals 3. I can see that as x approaches 3 from the left, the y values are heading to a specific value. As x approaches 3 from the right, notice the y values are going to the same place. It happens to be this point right here. Remember, we calculated that to be 2. If I look at the table of values, notice what the calculator says at x equals 3. At x equals 3, it says there is an error. What that simply means is that when we plug in 3 into the original function, it's recognizing that discontinuity. Technically, what's happening on the graph, you have a hole in the graph at the point 3, 2. Very difficult to see on the graphing calculator because it's smaller than a pixel, so we can't pick it up, but we can certainly recognize that there's a hole in the graph from our analysis. So when we cancel and remove that factor x minus 3, it creates a removable discontinuity in the function. That means the limit still exists. We can say the limit or the general behavior of the y values around 3, they're all heading to 2. However, because we could not factor out and cancel the x in the denominator, we have a non-removable discontinuity or a vertical asymptote in the graph. In this case, since both sides went in opposite directions, the limit did not exist. By the way, if our function had looked something like this, and both sides approach infinity as x approaches our target value 0, we would have said the limit is infinity. So just keep that in mind as a variation of those problems. All right, that was a tough one. Lots of analysis to think about there. Let's move on to problem 10. Now keep your calculator handy. We're going to need it on this problem. It says the cost to transport a mobile home depends on the distance, x, in miles that the home is moved. Let C of x represent the cost to move a mobile home x miles. One firm charges as follows. So our cost function, C of x, is dependent on x, which is the number of miles. And this is a piecewise defined function. So they charge differently based on the number of miles driven. So question A, find the cost to move a mobile home 111 miles. We're not going to plug x equals 111 into all three of those lines, just the one where 111 fits in the restriction. Notice 111 is between 0 and 200. So I'm going to be using this line to calculate the cost. We multiply 4 times 111. Now plug that into your calculator. That one I think I can do mentally. This gives us $444. Okay? Question B is a similar technique. We have to figure out where does this x value fit in the appropriate restriction. So this time we're looking at x equals 200 miles. Now in the piecewise defined function I have 200 in two places. But notice on that first line I have this inclusive inequality that says x can equal 200, whereas on the second line 200 has to be strictly less than x. So x equal to 200 fits on that first line. So I will be using this rule again. So we're going to take 4.00 times 200 miles. We're going to end up with $800. Okay? So to use a piecewise defined function, Figure out where your x value fits in all of those restrictions and use only the line indicated by that restriction. So the next x value here is 256 miles. So we have to figure out where does 256 fit within those restrictions. Clearly, 256 is between 200 and 300, so I should be using this line to calculate the cost. We have 3.75 times 256. I'm going to pop over to my calculator here to evaluate that. 3.75 times 256 gives us 960. So the cost in this case, 960. Are you getting the hang of it? All right, let's continue. Next value is x equals 300. So I have to figure out where does 300 fit in my restrictions. So 300 appears in two places in this piecewise defined function, but we're only going to use the middle line because that allows for the possibility that x equals 300. On the last line, 300 is strictly less than x. So 300 fits on that second line. We're going to use 3.75x for our function rule. So 3.75 times 300. Again, I'll pop over to my calculator and evaluate this. 3.75 times 300 gives us 1,125. So the correct value, make sure you include your dollar sign there to indicate units, 1,125. 425 miles is the next x value. Notice 425 is greater than 300, so I'm going to be using this last line. 3.25 times 425. Looks like the cost decreases the more miles that you go. 3.25 times 425 gives us a value of $1,381.25. So far, so good? Last question says, where is c of x discontinuous? We're basically looking for where are the breaks in this function. Well, if I look at the endpoints of these intervals, that's where I'm going to locate the discontinuities. So notice at 200, we have a break in the function. We know that the function value for x equals 200 is calculated by this line. If we were to plug 200 into the second line, those values would not match. That creates a break in the function. So c of x is discontinuous at 200. Similarly, at 300, we have a break in the function. If I plug 300 into both lines, I do not get the same value. Again, we have a break in the function. So this c of x function is discontinuous at 200 and 300 miles. All right, let's work a couple more problems, and then we'll take a break. Number 11 and 12, we're heading towards derivatives, which is why we spend so much time studying limits and continuity. It says find the average rate of change of the function y equals square root of 5x plus 1 over the interval from x equals 0 to x equals 3. Read carefully when you're taking your midterm. Sometimes we'll be calculating average rate of change. Later on, we'll be calculating instantaneous rate of change. So those are two different calculations. To find the average rate of change from A to B, we use the formula f of B minus f of A divided by B minus A. That should look really close to your slope formula, right? We're calculating the slope of the secant line that contains those 2 points. So f of b in this problem corresponds to f of 3. So f of the second given x value minus f of the first divided by the difference between the two. And by the way, I'm viewing this function as f of x. So to evaluate f of 3, I'm going to plug 3 into my function where I see the argument. This is going to give me square root of 5 times 3 plus 1 minus, now let's evaluate the function at our other x value. This becomes the square root of 5 times 0 plus 1. And notice in the denominator, 3 minus 0 is equal to 3. Evaluating our radicands, we have 15 plus 1 under the first radical. That's the square root of 16. We have 0 plus 1 under that second radical. That gives us square root of 1. And the denominator is still 3. If we simplify our radicals and evaluate, we come up with average rate of change. All right, one more problem for this video, number 12. Consider the function f of x equals x squared plus 5x. Use the definition of the derivative, which is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h to find f prime of x. You will have one problem on your midterm where you have to calculate a derivative by definition. The problem will be stated just like it is here on number 12. That means I will give you this formula for f prime of x. You do need to demonstrate all the steps in calculating the derivative by definition. You can certainly check it with your shortcut rules. So let's give it a try. F prime of x is equal to the limit as h approaches 0. We're going to have a big fraction here. First of all, we need to calculate f of x plus h. So this says go to the function f. Here's my function f over here, right? And plug in x plus h for that argument. So everywhere I see an x in the function rule, I'm going to replace it with x plus h. We end up with x plus h squared plus 5 times x plus h. Okay? So that takes care of the first term in our definition. Then we are to subtract. Let's subtract f of x. Well, f of x was simply our given function. So f of x is this function rule right here. Now watch this. If I simply write it there, I've only subtracted the first term in f of x. I need to subtract all of f of x. So make sure you get that expression in a set of parentheses. And we have a little bitty h here in the denominator. It's set up correctly. We have f of x plus h minus f of x divided by h. So we are set up and ready to go. Next, I need to simplify using algebra rules and then see if I can evaluate this limit. Notice I cannot plug h equals 0 into this expression directly because that gives me a 0 in the denominator, a usual problem. So let's work on this. We need to FOIL x plus h quantity squared. Now be careful here. Don't just distribute that 2. Think of x plus h as x plus h times x plus h, and then apply your FOIL process, right? So the product of the first two terms is x squared. Outside terms, we have plus xh. Inside terms, same thing. We combine those to get plus 2xh. And then the product of our last terms here, h times h, is h squared. Next, we're going to distribute the 5 into this binomial. We get plus 5x plus 5h. And distribute the negative into this set of parentheses. We get minus x squared minus 5x, all divided by h. Now, at this point, everything without an h should cancel. If it doesn't, you probably have a mistake that you need to hunt down. So let's inspect this. Notice x squared minus x squared, those terms do not have an h and they cancel. 5x minus 5x, those terms do not have an h and they cancel. Every term that's left has an h. So on our next step, let's factor it out as a GCF, greatest common factor. Factoring h out of the numerator, we have 2x plus h plus 5 left behind, and a little h left in the denominator. Remember that h in the denominator is what's causing the problem of me having a 0 in the denominator, but now it beautifully cancels away, and we can evaluate the limit by direct substitution. So we have limit h approaching 0 of 2x plus h plus 5. We can now evaluate this by direct substitution. So replacing 0 for the h and dropping our limit operator, we have arrived at our derivative, which is 2x plus 5. Now, if you have been studying and you've learned your rules of differentiation, if you go back to the original function and apply the power rule and the derivative of a constant multiple of x, wouldn't you end up with 2x plus 5 in one step? Absolutely. Remember, you will have one problem like this on the test where you have to demonstrate a derivative by definition. Be sure you're prepared for that. Now, understand the terminology. On the previous problem, we were finding the average rate of change. We used this formula. On this problem, we were finding a derivative. A derivative represents an instantaneous rate of change. So don't overcomplicate this problem. It says, what is the instantaneous rate of change of f of x at x equals 1? That's a really fancy way of saying find f prime of 1. Remember, f prime of x we found on part 12a. That's the derivative. It represents the instantaneous rate of change. So all I have to do is plug 1 into the derivative I calculated, and we come up with 7 for our instantaneous rate of change. All right, I think you need a break. So take a break. We will start with number 13, differentiation by our shortcut rules, in the next video. Thanks for listening.